This video will discuss the first part of MGSE 9 through 12 G.C.5. Derive using similarity the fact that the length of the arc intercepted by an angle is proportional to the radius, and define the radian measure of the angle as the constant of proportionality. This portion of the standard serves as the introduction of the radian measure to students in the geometric content, as well as the introduction to calculating arc lengths. The second part of the standard, Derive the formula for the area of a sector, will be discussed in video MGSE 9 through 12 G.C.5 Part 2. 7th grade was the last time that students officially investigated the area of circles, where they used the area formula, and they also focused on circumference of a circle using the formula circumference is 2 pi r. Interestingly, in Unit 4 of the 7th grade Georgia frameworks, the task Saving Circumference introduced students to measuring units in terms of diameter or radii, which will become the basis for radian measure in trigonometry. Because the 7th grade task is an effective way for students to think more deeply about the relationship between pi, diameter, and circumference, it could be revisited for students who are struggling with the understanding of this relationship prior to having them address GC5 and the other high school standards which are dependent upon a foundational understanding of this relationship. In the 8th grade, students once again applied the formula for area of a circle indirectly as they computed volume of different solids. This standard focuses on how an arc formed by an angle is related to the radius and angle measure. It introduces formally the radian measure. It is defined as the constant of proportionality, arc length divided by radius, as students investigate the relationship between the length of the radius and the length of the arc intercepted. But conversions between degree measurement and radian measurement are not expected in this course. The standard also calls for the development and understanding of the formula for the area of a sector of a circle. Again, this portion of the standard will be addressed in video MGSE 9 through 12 G.C.5 Part 2. We could begin this standard investigation using a concentric circle diagram, such as the one on the screen. The circle's radius starts at 2 units and increases by 1 unit in each concentric circle. The measure of the angle formed by the radii is 60 degrees. What's the measure of each arc in degrees? And if you could cut the circle and straighten out the arc, will each arc have the same length? Students could use this activators to set the stage for the standard, as it will allow them to recognize, without calculating the length of the arc, that the arc length is dependent upon the length of the radius. This video will look at students engaged in 2 tasks, one which is included in the Georgia frameworks, while the other is a derivation of a task that is included in the Georgia frameworks. The first task being the lifting the rope task, which can be used to review the relationship between the radius and the circumference of a circle. Students will formalize and perhaps discover the impact that an increase in the radius might have on the circumference. This task will begin as a discovery task, and then we'll revisit it as a partner task to formally address similarity of circles and circumference. Students are posed with the scenario. Imagine wrapping the circumference of a tennis ball and a basketball with pieces of string so that the pieces of string wrap perfectly around the balls. Now imagine lifting the entire piece of string 1 foot off each of the balls. Students are asked to determine which ball requires more string to close the circle that is 1 foot off the ball. This task allows students a hands-on approach to model the mathematics and to make sense of a problem and persevere in solving it.
Between this and 1 foot. Technically, this one would have more of a difference between this diameter and the 1 foot off the ball?
Well, it's circumference of basketball over circumference of basketball.
They would have the
Plus one
same.
foot.
They would be the
Which
same
ball
distance.
requires more string?
They're the same difference, but there's a lot bigger difference from this circumference plus a foot.
But that's not even what it's asking. It's asking how much string will it require to close it.
But
So it's probably
asking-
going to be the same now thinking about it because there's going to be 1 foot off. You close that 1 foot.
It's
There's-
not going
there's
to
a
be the
greater
same
difference.
because the
There's-
circumference of the basketball is bigger than
Yes, but
Because like
if it's
that's
one
a foot.
and then if it's a
if
foot
it's a
off
foot
of
off of
there,
this one.
then
But
it's
there's
gonna,
the space in the
But
middle.
look,
Yeah, I know, but to close it is going to require the same amount of string.
why?
So are you saying to close it, it's going to be the same amount of string between the tennis ball and what you have to close with the basketball?
Yeah,
And you're saying it's not. So let's hear you say why you think it is.
because it's going to be 1 foot off of it no matter what. So when you close it, it's having to close that 1 foot. Either way with that too.
So can you show that to me numerically? If I said prove it?
I don't know what numbers we would use really. Like,
I think they'll have the same ratio because it's basketball, the diameter or circumference of the basketball over the diameter, the circumference of the basketball plus a foot.
The students now take the challenge of their teacher to numerically prove their assumption.
Wait, are we trying to find like a formula or something that
No,
says
we're
no
trying-
matter what these numbers are,
100.48.
we're trying to prove that it's going to be the same distance towards it.
But
like
it should
closing
work
it.
like no matter what these numbers are.
Yeah, the ratio should be the
Like,
same.
find,
So
find
now
the
if you-
difference in a big
Now,
minus
so
small.
if you subtract
100.48 minus 25.12.
The circumference of the small circle for this circle is 9.2. I mean,
75.36.
Really?
Yeah.
wait, try it again using different numbers.
But those are completely random numbers. It's going to be the same.
So
It'll take the same amount of string, and the string will be 75.36 inches divided by 12, 6.28 feet.
And what is 6.28 in terms of pi? What's pi?
3.14.
So what's 6.28?
It'd be double that. It'd be 2 pi.
2 pi.
Yeah, 2 pi.
So what does it take to close it if I increase it by a foot or an inch? How much did you determine it took?
5.36.
But you divided that and got what?
6.28.
Which is actually,
2 pi.
Did we just find a formula?
I think you found a relationship of what it would take.
This standard introduces students to the concept of a radian measure. In the following clips, students are engaged in a task which is a derivation of the Georgia Framework's task, arcs, strings, and radii. This task is called Exploring the Radian Measure, and like the task, arc, strings, and radii, it allows students to see the radian as the constant of proportionality between the length of the intercepted arc and the radius. The teacher in this task will lead her students through a scaffold approach of the task in a small learning group. The level of teacher facilitation in this task could vary based on the students involved in the activity. Students will begin the task using a compass to construct a circle, marking the center and radius of a circle. It's important that all group members choose a different size of circle. Differentiation ideas for this task include providing students with pre-cut circles and having them locate the center and radius of the circle, or providing students with pre-cut circles in which the center and the radius have already been marked. Once students have constructed their circles, have them cut them out and supply them with a pipe cleaner or string to mark the radius of the circle, and then use that radius to mark all the distance around the circle in radius lengths. What are you doing next, Connor?
Beginning at the point where your radius intercepts the circle, wrap your string around the circumference of the circle and mark where one length of your radius ends.
How many times did you guys figure out that you could wrap your radius around your circle?
About 6.5 times.
What if I told you it was exactly 6.28 times? 6.28 mean anything to you?
No, ma'am.
What about 3.14? Does that mean anything to you? Well, what happened if you doubled pi?
6.28.
So how many pies would your radius wrap around your circle?
Twice.
2 pies. Students will use 2 consecutive radii as marked on the circle to construct a central angle. They will then use their protractor to measure that central angle. What did you guys come up with as its angle about?
Around 55 through 60.
Can anybody get a little more precise?
Probably around 59.
59? All right, let's cut it out. So there are your central angles that you just cut out. The teacher then provides a pretty direct instruction moment to get students to compare the central angles that they have created. All right, now let's slide it down so that all the vertices, all those vertex pieces line up. What do y'all notice? They do have the same angle. And you all measured it. It was about 57 degrees when you measured it. But you all drew your own circles. How did y'all come up with your sides of your angle?
The radius.
The radius. And then how did you come up with this part of your circle right
We
here?
used the radius and measured the circumference.
So this length on the outside of your arc was equal to your radius. Is that correct? And this radius, well, it was equal to itself. And everybody had a different radius. Everybody had a different length of the arc, but everybody ended up with the same angle. That's what a radian is. This angle measure is 1 radian, and that's going to happen anytime your radius is equal to the arc. That's equal to 1 radian. Students can also explore the radian measure through the use of technology. The GeoGebra applet featured on this screen allows students to manipulate the radius of the circle and explore that relationship with the arc that is created. Students are asked guiding questions to help establish the relationship. Students may also discover the radian measurement through the Desmos activity also featured on this slide. Students can manipulate the radius of the circle as well as the central angle of the circle. Additional resources along with lesson plans can be found at the LearnZillion link featured on this slide. Students might also be interested in the history of the radian measure. Resources to address the history of the radian measure are also featured on this slide.